helper who is going to be here to be able to start the video. So it's my pleasure to welcome everyone to the Fairness and Ranking and Recommenders tutorial. And this tutorial will be given as a pre-recorded video. And the presenters are Evi Petura from the Computer Science Department at the University of Ioannina, Georgia Kutrika, who is Research Director at the Athena Research Center, and Konstantinos Stefanidis, who's Associate Professor at the Faculty of Information Technology and Communication Sciences of the Tampere University in Finland. And so I want to thank you, everyone, all the attendees and the panelists. And so let's go ahead and get started. And I guess just a reminder that if you have questions, you can enter them in Q&A and I'll curate them. And then at a good breaking point, we'll go ahead and ask them, or else you can send them on Slack. Okay?
Yes. So, hi all, I think Book is trying to start the videos. Sorry for the delay. We had we have two actually student helpers in the session, Book and oh, there he is. Okay, there you are. Okay, fantastic. So this is going to be, the tutorial is going to be in 4 different videos. I guess we can start with the first video playing and gather questions as we go along. And maybe in between the different videos, we can discuss the questions that came up in the different parts of the tutorial, right? Okay, and of course, the tutorial presenters are here and they can answer questions and so on. Evi, Yuli, Costa, are you here with us? Can you hear me? Yes. So can one of you say a few things about the tutorial, what is going to cover? Maybe I cannot. No. See if I can. I don't have the permissions. Evie wants to say something. I don't have the permissions to change, to unmute you, but.
Can you hear me now?
Yes, yes, we can. Thank you.
Hi, everyone. I'm Evi Petura. I will be presenting the first 2 parts of the tutorial. So please, if you have any questions, you can ask them at the end of the part 1 or part 2. So I would like also to thank the tutorial chairs for giving us the opportunity to give this talk at ICD. Okay. So I hope you find the presentation interesting.
Thank you.
Welcome to the tutorial on fairness in ranking and recommenders. I'm Evi Petura and I will be presenting from Ioannina, Greece. Then Konstantinos Stefanidis from the University of Tampere will continue, and we return back to Greece, and Georgia Kutrika from the Athena Research Center in Athens will conclude the presentation of this tutorial. So, why should we care about algorithmic fairness? We live in a world where decisions are assisted or even taken by algorithmic systems driven by a large amount of data. And this concerns personal decisions from simple or not that simple ones, like where to eat, who to date, what are the news, and so on. But also not just personal decisions, but also decisions about insurance, credit, housing, pricing of goods and services, and so on. This raises concerns regarding how much can or should we trust such systems. And there have been numerous studies regarding fairness in decision support systems. For example, what images do people choose to represent careers? For instance, when we Google doctor or we Google nurse, what is the percentage of images portraying women that we get in the result? A study a few years ago has found evidence for stereotype exaggeration and systematic underrepresentation of women when compared with the actual percentage as estimated by the US Bureau of Labor and Statistics. Two interesting conclusions from the study were that the people prefer and rate search results higher when these results are consistent with stereotypes. Another interesting result was that if you shift the representation of gender in image search results, then the people's perception about real-world distribution tend to shift as well. Another well-known example is the COMPAS system. COMPAS is a commercial tool that uses a risk assessment algorithm to predict some categories of future crime. This tool is used in courts in the US for bail and sentencing decisions. It was found that the false positive rate, that is the people who were labeled by the tool as high risk but did not reoffend, was nearly twice as high for African American as for white defendants. There are many more case studies. For example, names that are used by men and women of color are much more likely to generate ads related to arrest records. Also, using a tool called Ad Fisher, it was found that if you set the gender to female, this will result in getting ads for less high-paid jobs. Evidence for bias also exists in word embeddings. For example, the vector that represents computer programming is closer to men than to women. And many more studies. Okay, so what causes this bias? Data may be incorrect and incomplete. That may be poorly selected, incorrect, outdated. Also, data reflect and promote historical biases. There is also issues of size disparity. Most systems learn on a majority, which may result in errors concentrated in the minority class. Also, algorithms are very often seen as black boxes. Their output models are hard to understand. They may make unrealistic assumptions. They may not compensate for problems in the input data, and so on. So this creates a bias reinforcement cycle. In the remaining of this part of the talk, I will introduce some basic concepts regarding fairness. In part 2, I will talk about fairness in ranking. In part 3, Kostas will talk about fairness in recommenders. And in the last part of this talk, Georgia will talk about fairness in other systems and present our conclusions. So fairness is defined in general as lack of discrimination. It's very often associated with one or more protected attribute, and the output of the algorithm should not depend on the value of these attributes, and any differences should be explained by other attributes. Such protected or associated attributes may be, for example, gender, sex, and so on. There are in general two approaches for defining fairness, individual fairness and group fairness. Individual fairness is based on the premise that similar people should be treated similarly. To operationalize fairness, we need to define what similarity of individuals mean and what similarity of output means. To formalize similarity of individuals, we can use a distance metric. This distance metric must be task-specific. That is, individuals may be similar for one task, but not similar for another. This should express ground truth. It should be public and open to discussion, and it can be externally imposed, for example, by a regulatory body or some other organization. Now, how we define similarity of treatment depends clearly on the algorithm. For example, let's see an example. Say we have a classifier that maps individuals to outcomes. And we have randomized mappings, meaning that to classify an individual X, which is an outcome according to some distribution depending on X. A way to define individual fairness in this case is to ask that the distance between the probability distributions of the output for two individuals is close when their distance is close. The other type of fairness is group fairness. In group fairness, individuals are divided into groups based on the value of one or more of the protected attributes. For example, if we have one binary protected attribute and the privileged value is 1, then we have two groups, the non-protected group or the privileged group and the protected or the minority group. Now, group fairness requires that all groups should be treated similarly. Again, we need to define similarity of treatment. Let's see an example again using classification. Say that we have the data set that you see in the left of this figure, and assume that color is the protected attribute and red is the protected group. And we have the predicted output that you see on the right of this figure, and the favorable outcome is yes. We should define now, given this output, whether this classification is fair. Before going into details about group fairness, let's make the following notice. The simple approach of hiding the value of the protected attribute does not work because the protected attribute may be correlated with other attributes. Let me also make a distinction between disparate treatment and disparate impact. Disparate treatment refers to the illegal practice of treating an entity differently based on a protected characteristic. Whereas in disparate impact, the outcome does not depend on the protected attribute, even if the outcome depends on the protected attribute, even if people are treated the same way. This was solidified when a power company asked for a high school diploma for unskilled work, thus excluding black applicants from taking the job. Another note is between different views of fairness. So the non-discrimination view of fairness seeks to allocate resources in a way that does not consider irrelevant attributes, where the equality of opportunity view on fairness seeks to correct a historical or present disadvantage for a group. Most definitions of fairness can be adapted to work for non-discrimination and equality of opportunity. Now, group fairness definitions can be divided into three groups: base rates, group conditioned accuracy, and group conditioned calibration. Group fairness based on base rates compares the probability of a favorable outcome for the non-protected group and the probability of a favorable outcome for the protected group. We have different ways to compare these two probabilities. We can take the ratio, which is the approach most commonly used, or we can consider their difference. An interesting case is when we ask for the rate for this ratio to be equal to 1. This is known also as demographic parity or statistical parity. And this form of fairness preserves the input ratio, that is, the demographic of the individual receiving a favorable outcome is the same as the demographics of the underlying population. The probability that you get a favorable outcome does not depend on the group that you belong to. And here is an example where the outcome preserves demographic parity. Another well-known form of group fairness based on base rates defines that we have unintended discrimination or disparate impact when this ratio is smaller than a value t being 0.8, which is a generalization of the 8% rule for equal opportunity. A common criticism of group fairness is that it ignores the utility or the goodness of each individual in the group. This may result in a self-fulfilling prophecy. This means that by deliberately choosing the wrong member of the protected group, we make a bad track for the protected group. And also to reverse tokenism, which means that by denying access to a qualified member of the privileged group, we create convincing refutations. So most of the metrics that we're going to see about fairness in ranking take into account utility as well, besides the base rates. Now, to conclude, there are other definitions of fairness. For example, there are the other two types of fairness for groups is classification accuracy, which considers the performance of the classifier. For example, whether the classification errors are the same for each group, and calibration-based group fairness, which is about probabilistic classifiers, which output the probability that an individual belongs to the positive club. And we need these estimates to be well calibrated. Finally, another form of fairness is counterfactual fairness, where a decision is considered fair towards an individual if this decision is the same in both the actual and the counterfactual world, where the individual belongs to a different demographic group. And causal inference techniques are used to express counterfactual fairness. And this is the end of the first part of this tutorial. Thank you. Welcome to the second part of the tutorial on fairness in ranking and recommenders. In this part of the tutorial, we'll be talking about fairness in ranking. In many applications, the output is a rank list where the items are ordered in descending order of some measure of their relative quality. Such applications are, for example, search engines, newsfeed, recommenders. The quality of an item or the utility of an item most often is the relevance of the item for the input query. This relevance is commonly expressed with a relevance score. Formally, a ranking is an assignment, a mapping of items to ranking positions. An issue with ranking is that people tend to look only at a few top results. This is known as position bias. Now, as in fairness in general, similarly with fairness in ranking, we have two general approaches. Individual fairness, where items with similar relevance score should receive similar visibility. Where visibility, we may think of visibility as assignment to similar positions in the ranking, and group fairness, where all groups should receive similar visibility. Let's now see how these notions have been formalized. One way to formalize fairness constraints in the case of group fairness is through fairness constraints. So given a number of protected attributes or properties, fairness constraints specifies an upper bound and a lower bound on the number of items having this property that must appear in the top k positions of the ranking. For example, we can specify that we want at least one item with property red in the top 4 positions. Another way to specify requirements of fairness is through discounted cumulative fairness. Discounted cumulative fairness focuses on the representation, the number of items of the protected group in the top P ranking positions for different values of P. The idea is built on discounted cumulative gain, a measure very often used to evaluate the quality information retrieval in terms of relevance. in DCG, what we do is we sum up the relevance of the items starting from the top item in the top position, and we discount the relevance of the item with the logarithm of their position. In the example in the figure, the discounted cumulative gain at position 4, we sum up the relevance of the item in the first position, then the relevance of the item in the second position discounted by the logarithm of 3, and so on, up to the item in position 4. Building on this idea, normalize discounted difference, accumulate the number of items at discrete positions in the ranking, and discount these numbers accordingly. For example, say we choose positions 5 and 10, we sum up the number of items up to position 5, 2, and we discount that with the logarithm of the 5, the logarithm of the position 5. Similarly, we count the items up to position 10, and we discount this number by the logarithm of position 10. We have two other variations of discounted cumulative fairness: normalized discount ratio, which is similar with normalized discounted difference, but the only difference is in the denominator, where now we sum up the numbers of items that belong in the non-protected group. The third measure is normalized discounted KL divergence, where we use the KL divergence to compute the difference between the members' probability distribution of the protected group at the top positions and in the overall position, in the overall population. A problem with these measures is that minimal difference in relevance scores may translate into large differences in visibility or exposure because of position bias that results in large skew in the distribution of visibility or exposure. To address this fact, fairness of exposures uses a position discount vector, V, where Vj represents the importance of position j. For example, the fraction of users that examine an item at position j. They also consider probabilistic ranking. The probabilistic ranking of n items in n positions is an n-square matrix, doubly stochastic matrix. The rows correspond to items, the columns correspond to positions, and Pij is the probability of item I being ranked at position j. Now, given the position discount vector and a probabilistic ranking, the exposure of an item in the probabilistic ranking P is the expected visibility of the item, and the exposure of the group is the average exposure of the items that belong to the group. Given this definition of exposure, we can have different definitions of fairness. For example, demographic parity that asks that the two groups get the same average exposure. Disparate treatment, where we ask that the exposure, the treatment for the two groups are proportional to their average utility. And then disparate impact, where we ask that the impact for the two groups are proportional to their average utility. Now, a way to express impact is through the click-through rate, which also depends both on exposure and the relevance of the ad. So far, we have seen group-based measures of fairness. Equity of attention is an individual approach to fairness, which asks that each item receives attention proportional to its relevance. So it's an idea similar to fairness of exposure, but applied to individual items. However, it's very difficult to achieve equity of attention in any single ranking. For example, think of multiple items having similar relevance. It's not possible to place all these items in the same ranking position. But if we have a sequence of ranking, then we can achieve somehow some form of amortized attention, equity of attention. And exactly, this is exactly what equity of amortized attention does. So given a sequence of rankings, we say that this sequence offers amortized equity of attention if each item receives cumulative attention proportional to its cumulative relevance. So we have somehow a fairness requirement over time. We can also count unfairness, that is how much a sequence violates equity. And the way to do that is through KL divergence. So computing the KL divergent between the empirical distribution of attention and the empirical distribution of relevance for this sequence of ranking. So to sum up, we have seen a variety of definitions for fairness. Some of them are set-based and some of them are exposure-based. In terms of set-based, we discussed the fairness constraints and a number of cumulative-based metrics. All of them are group-based. In terms of exposure-based metrics, we showed both group-based metrics and individual metrics. And also we saw metrics that achieve fairness over time. Now let's talk a little bit about how to achieve fairness. In general, methods for achieving fairness in ranking and in recommenders can be distinguished as pre-processing. Pre-processing approaches transform the data so that any underlying bias or discrimination is removed. In processing approaches that modify an existing algorithm or introduce new algorithms that result in fair ranking and recommendations. And post-processing approaches that treat the algorithms as black boxes and modify their output to ensure fairness. In general, we are going to see some interesting pre-processing approaches, some generic techniques for pre-processing approaches in the recommender part of this tutorial. So in this part of the tutorial, we'll focus on in-processing and post-processing approaches for ranking. The in-processing approaches for ranking, of course, depend on the ranking algorithm. We will discuss two different types of ranking algorithms, learning to rank algorithms and algorithms based on linear ranking function. In learning to rank algorithm, we obtain a ranking function that is learned by solving a minimization problem with respect to a loss function, which most often this loss function is a measure of the accuracy of the estimated ranking with respect to the training data. The training data may be pair of items, item score, ranked list. The general approach of making learning to rank algorithms fair is by extending the loss function by adding an extra term to ensure fairness. Let's see an example. The delta-art approach builds on the ListNet learning to rank framework. The ListNet learning to rank framework is the list-wise. That is, the training set is a list of documents ordered by their relevance to an input query. And they learn a ranking function that minimizes a loss function that considers the difference between the expected ordering of the documents and the ordering of the items in the training set. So delta R extends the loss function of the ListNet framework by an unfairness term. Gamma in the term is a parameter that controls the desired trade-offs between the utility, the accuracy of the ranking, and fairness. Now, for fairness or unfairness, the authors use a a measure based on democratic, on fairness, on parity based on exposure. So they consider the exposure received by the protected group and the exposure of the unprotected group. Another approach that extends learning functions so that they're fair is based on learning fair representation, and it extends a learning algorithm proposed for fair classification. The basic idea in this line of research is to introduce an intermediate level between the input space and the classification output. Z is a fair representation of the input in that it best encodes the input and also hides any information about membership in the protected group. Formally, Z is a random variable of size k, where each of the k values represent a prototype. So each item in the input is mapped in one of the k prototypes. The loss function consists of three terms. The first term ensures the quality of the encoding, that is that the distance of the input points to their representation is small. The second term ensures fairness. And the last term, accuracy, that is ensures that the prediction based on the representation is accurate. AX, AZ, and AY are all hyperparameters that control the trade-offs between quality of the encoding, fairness, and accuracy. For fairness, statistical parity is used. Now, this method can be extended to be applied to ranking as well by just changing the third term to express, instead of accuracy in classification, accuracy in ranking. Asking that the distance between the ground truth ranking and estimated ranking is small. We can use any type of distance to express ranking accuracy. Now, another kind of ranking is achieved through linear ranking functions. In this case, we have for each item, there is a number of scoring attributes, and their score is computed using a linear ranking function that uses a weight vector to compute a goodness for each item. In this case, we can make this linear ranking function fair by asking that we modify f to produce a fair f star with weight vector such as the distance between the weight vector of f fair f star is as close as possible to the original f. Now let's move to post-processing approaches. We will see two different ways to do post-processing. One that uses a generative process and one that uses constraint optimization. The generative process uses a fairness parameter f that specifies the desired relative fairness of the two groups. And the approach is as follows. We start to build the new ranking by initializing it to an empty list. For each position j in the new ranking, we perform a Bernoulli trial with probability f, and if the trial succeeds, we select the best item, the best available item from the protected group. If the trial fails, we select the best available group from the best available item from the non-protected group. So when f equals to 1, we select all items only from all items in the protected group precede all items in the non-protected group because the trial always succeeds. If f equals to 0, the opposite, and if f is larger than 0.5, then the items in the protected group are preferred over the items in the non-protected group. And let's see an example. So the ranking is in the left is the original one, and say that we want to re-rank the original ranking using F equal to 1. Then at each position, the red items succeed. So all red items precede the blue items. When F is larger than 0.5, then at each position, the probability of selecting a red item is larger than the probability of selecting a blue item. Note that the relative order of two items that belong to the same group is not changed. The other approach, FAIR star also presents a statistical test for this generative model that given a ranking determines the probability that the ranking was generated by the model. That is that the ranking was generating using the model with parameter F star equal to F, or whether the ranking was generated with a parameter smaller than F, which would mean that the protected group is represented less than desired. The other approach of post-processing is based on forming a constraint optimization problem, and there are many variants of this. For example, given a utility definition and a fair ranking definition, we want to re-rank the items so that we maximize the utility and get a fair ranking. Or we may want to specify a different constraint. For example, we may want to maximize fairness and also keep the distance, the utility of the re-ranked list as close to the utility of the initial rank as possible, or smaller than a given threshold set. And this approach has been applied for exposure, for fairness of exposure. It has also been applied for to achieve amortized individual fairness. There is both an offline and an online version, and it has also been used in case of having fairness constraints. Okay, so to summarize, approaches to fairness in ranking depend on the definition of fairness and on the ranking algorithm. For in processing, we have seen two different approaches. One, applicable to learning to rank, through extending the objective function or through introducing a fair intermediate representation, and one applicable to linear preference functions by adjust the weights. For post-processing approaches, we have seen two different ones, one based on a generative process and one that formulates a constraint optimization problem. Finally, a final remark, diversity is different than fairness in ranking because diversity has different objectives. For example, to cover different user intents as well as address query ambiguity, and also diversity wants to make results more informative and interesting by avoiding redundancy and supporting serendipity and novelty. And this is the end of part 2. Thank you.
Okay, so I would like to ask if there are any questions. Any of the participants can raise their hand before we start the next part.
Chris, I think there is one question posted in the Q&A section. It's regarding the, maybe I can repeat the question.
Oh, I see it. Okay.
Oh, yeah. Okay, please go ahead. Yeah.
Okay, yeah. Thanks for pointing that out. So the question is regarding the relationship between individual fairness and group fairness. Is individual fairness a stronger constraint compared to group fairness, meaning that individual fairness guarantees group fairness? So let's see. So Avi, do you want to take that? Here, let me.
Okay, sure. Okay, actually, this is an interesting question, and actually, group fairness and individual fairness take a different point of view in fairness. So individual fairness considers the merits of each individual. So you can have individual fairness and not group fairness. For example, I think of the case that we do not have enough qualified people in the protected group. Then you may have individual fairness because you don't have enough good people, but you don't have a group fairness because you don't have enough people to satisfy statistical parity. And group fairness is not equivalent with individual fairness because group fairness totally ignores the merits of each individual. For example, the accuracy of each individual item. So there are two different views of fairness, which are not equivalent.
Okay, so thanks a lot for that answer. Any other questions before we move on? Okay, I don't see any hands raised. Let me just check Slack really quick. Yeah, nothing on Slack, so I think we're ready for part 2.
Hello everyone, my name is Kostas Stefanidis. I'm an associate professor in data science at the Tampere University in Finland. And together we will continue on the third part of this tutorial, focusing on fairness in recommender systems. Inherent in the idea of recommendation is that the best items for one user may be different than those for another, and when trying to facilitate transactions, many recommendation applications involve multiple stakeholders, and this may give rise to fairness issues for more than one group of participants. At the same time, stakeholders have a varying level of familiarity and expertise with the system and the underlying technologies. So, regarding the different stakeholders for recommendations, we distinguish between consumers of recommendations, where recommenders care only for consumers' fairness, providers or producers of data items to be recommended, where fairness need to be preserved for the providers only, like, for example, making visible new sellers in an HSO. System owners, especially when owners are different to the providers of data, and auditors, like policymakers and governmental auditors. When comparing consumers and producers' fairness, we can say that producers' fairness is kind of passive, since producers do not seek out recommendation opportunities, but rather wait for users to come to the system and ask for recommendations. Moving forward, we can consider as well scenarios in which both consumer and providers are considered for ensuring fairness, like, for example, a rental property recommender, in which the recommender may treat minority applicants as a protected class and wish to assure that they are recommended properties similar to white renters. Or the recommender may also wish to treat minority landlords as a protected class and ensure that high-qualified tenants are referred to them at the same rate as to white landlords. Next, we will see specific methods on how to ensure fairness in recommender systems. So, as in the case of ranking, we distinguish between pre-processing, in-processing, and post-processing methods. Pre-processing methods can work with sampling or reweighting by generating weights for training. There are also methods that include learning. So, for example, that learn a probabilistic transformation for editing labels, and approaches that make unclear information about protected attributes. Also, we can have approaches that, based on a repair of the data, can remove disparate impact and approaches that add data to the recommender's input in order to improve fairness with a minimum accuracy loss. In-processing algorithms focus on designing algorithms that produce fair recommendations, mostly by using matrix factorization or alerting the algorithm's objective by adding regularization or even adding randomness in variational autoencoders recommenders. The motivation of the first approach comes from the STEM example that has to do with recommendation in education, in science, technology, engineering, and mathematics topics. So, according to some statistics, women accounted for only 18% of the bachelor's degrees awarded in computer science. The underrepresentation of women causes historical ratings data of computer science courses to be dominated by men. And based on this, the learned model may underestimate women's preferences and be biased toward men, leading to unfairness. In general, we can consider two forms of underrepresentation: population imbalance and the observation bias. In the first case, different types of users occur in a dataset with different frequencies. So, significantly fewer women can succeed in STEM than those who do not. However, more men succeed in STEM than those who do not. In observation bias, certain types of users may have different tendencies to rate different types of items. So, motivated by the STEM example, there is a matrix factorization approach that defines 5 different ways for counting unfairness, focusing on minimizing unfairness. So, for example, value unfairness counts the inconsistency in estimation errors across different user types, leading, for example, to have male students that are recommended STEM courses when they are not interested in STEM, while female students not being recommended even if they are interested. In turn, absolute unfairness counts inconsistency in absolute estimation error across user types. Also, 3 more definitions of unfairness: underestimation and respectively overestimation unfairness count inconsistency in how much the prediction underestimate or overestimate respectively the true ratings. Non-parity unfairness counts the absolute difference between the overall average ratings of disadvantaged users and those of advantaged users. Those definitions can be exploited at the end to augment the learning objective of traditional matrix factorization, simply to say as an additional part in the formulas. In a different approach, in a regularization approach, we can target at achieving recommendation or statistical independence. So here, in addition to users, data items, and recommendations, as in traditional approaches, we consider sensitive features, that is, information to be ignored in the recommendation process, like, for example, the gender of a user, the popularity of an item, and so on and so forth. So here, we need to have no information about sensitive feature that influences the outcome, as well as to select recommendation so as to satisfy an independence constraint. More or less, the core of this regularization approach is included in this formula. Here we have a regularizer to constrain independence, the so-called independence term. The larger value of this independence term indicates that recommendation outcomes and sensitive values are more independent. And there are several alternatives for the independence term, like, for example, the mutual information with histogram models or normal distributions, or even by exploiting distance measure. And here we can somehow visualize how to add a sensitive variable to a recommendation model so that it satisfies an independence constraint. In a different way, we can use variational autoencoders that were recently proposed as the state-of-the-art for collaborating filtering recommendations. This approach proposes incorporating randomness in regular variational autoencoders to increase, or in other words, to improve fairness when considering multiple rounds of recommendations. But how to do this? By adding a noisy component when sampling values from variational autoencoders late in the representation in order to provide long-term fairness in the next interactions, for sure paying the cost of a small decrease in the ranking quality. Moving forward to post-processing methods, we start with a calibration method that focuses on re-ranking, considering results as fair if they achieve fair representations. So, the game is between accuracy and calibration, and the fair representation is achieved via a diversity measure. Next, we continue with more post-processing methods, but now in the context of group recommendations. So, typically, recommenders provide suggestions adapted to the preferences of a single user. However, there are many scenarios in which the recommended items are consumed by a group of users, like, for example, a trip with friends, or a movie to watch with the family, or the music to be played in a car, and so on and so forth. Many times, the users within a group may be heterogeneous because people in a group have different preferences and interests. Most of works on group recommenders targets at maximizing the group's overall satisfaction with a recommended list. This way, there could be one or more users that do not like the items in the list. So, there is a clear need for fair group recommendations. Intuitively, in this case, fairness tries to minimize the feeling of dissatisfaction within the group members. So, one of the first approaches focusing on this problem assumes a measure for quantifying the satisfaction or the utility of a user in a group given a list of recommendations. More or less here, we care about how relevant the best recommended items are to the user. Based on that, and by averaging user utilities, we can have the group utility or the so-called social welfare. Then, for achieving fairness, we need to balance the utilities of the users in a group. Intuitively, a list that minimizes the dissatisfaction of any user in a group can be considered as the most fair. Several ways for computing the individual utility, that is the utility satisfaction of a single user. For example, we can just take the average of the relevant scores of the top k items for the user. In turn, for computing the social welfare, that is the utility for the group, we take the average of the individual utilities. For computing fairness, we compare the utilities of the users in the group, like the formulas we see in this slide, that exploit minimum, variance, or kind of average or min-max functions. And for locating the best suggestions, we try to maximize social welfare and fairness using this formula. A greedy approach for doing so is to select an item that achieves the highest fairness when it is added to the current recommendation list. In a different line of work, this approach resembles ideas from skylines. It represents items in space where each dimension corresponds to a group member and each candidate equals the relevance of the item for the user. So here, we need to define a dominance relation based on which an item I dominates an item I prime for a group if for each user I ranks at least as good as I prime and there exists at least one user for which I ranks better. So the top items not dominated by any other item are called Pareto optimal. In turn, the n-level Pareto optimal contains items dominated by at most n-1 other items. Thus, the top n suggestions are within the n-level Pareto optimal set. Since it is impractical to identify the exact set of n-level Pareto items, one approximation is to request top n prime recommendations for each user in the group, take their union, and select the n-level Pareto optimal items among the n prime ones. Moving forward, we target on constructing packages for groups. Fairness here can be defined with the concept of m-Proportionality. So for a user and a package, the package is m-proportional to the user if there exist at least m items in the package that the user likes. In turn, for a group, the m-proportionality of the package for the group is defined as the number of users for which the package is m-proportional over the total size of the group. In turn, we can use the notion of m-Envy-Freeness. So here, a user in a group is envy-free for an item in a package if the relevant score of this item belongs to the top ones. A package in turn is envy-free for the user if user is envy-free for at least m items in the package. For a group, the m-Envy-Freeness of package is defined as the number of users in the group for which the package is envy-free over the total size of the group. For maximizing fairness, the proposed algorithm constructs the package greedily, which means in rounds we can add to the package the items that satisfies the largest number of non-satisfied users. Additional category or distance constraints can be used. So for instance, when selecting an item from a specific category, we remove the items of this category from the candidate set. While in the distance case, we can consider as candidate items only the items that when added to the existing solution satisfy the distance constraints. In a different approach, here we study recommendations for groups when we have multiple interactions with the system, namely sequential recommendations. So let's assume a group of 5 in a movie recommendation scenario where the group interacts 5 times with the system. And in figure in this slide, we see the user satisfaction when following a traditional group recommendation approach, in which we use both the average and the least misery or minimum aggregation functions. As we can see, User 4, the yellow one, has a low satisfaction score in all iterations, almost no interesting recommendations. That is, the recommender is unfair to him or her, and unfairness continues throughout all 5 iterations. So, this method for making happier user 4 consider both satisfaction and disagreements in the group. For counting satisfaction for each user, we directly compare the user satisfaction from the group recommendations with the ideal case for that user and compute the average group satisfaction. For counting disagreements in the group, we count the difference in the satisfaction scores between the most satisfied and the least satisfied user in the group. More or less, for computing the importance score of an item, we take a weighted combination of the traditional average and minimum aggregation methods. The method includes a dynamic alpha weight that is different in each iteration and is computed by subtracting the minimum satisfaction score of the group members in the previous iteration from the maximum score. For example, for an extremely unsatisfied user in a previous iteration, alpha takes a high value and promotes that the user's preferences. And as a proof of concept, when applying this method, user 4, who has a low score of satisfaction in the first iteration, has better scores in the following. Thank you.
Hello everyone, I'm Georgia Koutrika. I am a research director at Athena Research Center in Greece. Let's continue now with the last part of our tutorial. We have talked about different concepts or aspects of fairness in recommender and ranking systems. We also talked about how to make these systems fair by changing the input data, the algorithm, or the output of the algorithm to remove bias or unfairness. Now, we are going to examine a more fundamental question: fairness as a program property. We are going to look at 2 concepts. How can we verify if a program is fair? How can we code in a fair-aware manner? Or in other words, how can we have fairness as a first-class citizen in programming? Algorithmic fairness is a question about programs and their properties. Is a program fair under some definition of fairness? Can we quantify how fair it is in some way? In program fairness verification, our goal is to analyze a given decision-making program and construct a proof of its fairness or unfairness. Just as a traditional static program verifier would prove correctness of a program with respect to, for example, lack of divisions by 0 or integer overflows. Tackling the fairness verification problem requires answering a number of challenging questions. What class of decision-making programs should our program model capture? Can we define the set of possible inputs to the program? How can we describe what it means for the program to be fair? How can we fully automate the verification process? A fairness verifier takes a decision-making program P and a dataset or population model M as input. Note that while using a concrete dataset simplifies the verification problem, it also raises questions of whether this dataset is representative for the population for which we are trying to prove fairness. On the other hand, a population model can be a probabilistic model that defines a joint probability distribution over the inputs of P. There are many ways to define when and why a program is fair or unfair. For example, if we want to prove group fairness where the algorithm is just as likely to hire a minority applicant M as it is for other non-minority applicants, our post-condition will be an expression of the form we see on the slide. The verifier then proceeds to prove or disprove that P is fair for the given population defined by model M. For simple definitions, such as group fairness, the verification problem reduces to computing the probability of a number of events with respect to the program and the population model. For more complex definitions, such as individual fairness, proving fairness requires more complex reasoning involving multiple runs of the programs, and this is a notoriously hard problem. In the case of a negative result, the verifier should provide the users with a proof of unfairness. Depending on the fairness definition, producing a human-readable proof might be challenging, as the argument might involve multiple and potentially infinite inputs. For example, in the case of group fairness, it might be challenging to explain why the program outputs true for 40% of the minority inputs and for 70% of the majority inputs. A different approach is to make fairness a first-class citizen in programming. In what is called fairness-aware programming, developers can state fairness expectations natively in their code and have a runtime system monitor decision-making and report violations of fairness. This approach is analogous to the notion of assertions, which are ubiquitous in modern programming languages. For instance, a developer may say that the value of X should be positive at a certain point in the code. However, the difficulty is that fairness definitions are typically probabilistic, and therefore, detecting their violation cannot be done through a single execution, as in traditional assertions. Instead, we have to monitor the decisions made by the procedure and then, using statistical tools, infer that the fairness property does not hold with reasonable high confidence. For example, consider a movie recommendation system where user data has been used to train a recommender that, given a user profile, recommends just one movie. Suppose that the recommender was constructed with the goal of ensuring that male users are not isolated from movies with a strong female lead. Then the developer may add the following specification to the recommender code, which says that male users, the procedures, recommends a movie with a female lead at least 20% of the time. To determine that the procedure F satisfies a fairness specification phi, we need to maintain statistics over the inputs and outputs of the procedure as it is being applied. Specifically, we compile the specification into runtime monitoring code that executes every time the process F is applied, storing aggregate results for every probability event appearing in a phi. For instance, in our example with movie recommendation, the monitoring code would maintain the number of times the procedure returned true for a movie with a female lead. A big challenge is checking individual fairness. In this case, the runtime system has to remember all decisions made explicitly so as to compare new decisions with past ones. Clearly, both program fairness verification and fair-aware programming are novel approaches that need further development. We have talked so far about fairness in decision-making processes, such as recommender systems and rankers. However, there are several other processes that the system needs to make decisions and where fairness is also important. There are several examples more familiar to the database community where fairness has been studied, such as cache allocation, multiple resource allocation, and scheduling. For example, inspired from classical economic theory, a fair resource allocation should have the following desirable properties. Sharing incentive, where each user should be better when used in the shared allocation setting than she would expect from simply having access to all the resources. Pareto efficiency says that it should not be possible to increase the allocation of a user without decreasing the allocation of at least another user. Strategy proofness says that the users should not be able to lie about their resource demands. M-Envy-Freeness says that the user should not prefer the allocation of another user. For example, in ROBUS, a cache allocation system, the fairness model is based on Pareto efficiency and sharing incentive. ROBUS groups queries in small time-based batches and employs randomized cache allocations on each batch. I would like now to conclude our tutorial with a few notes. The ranking and recommendation system has several applications such as hiring, lending, college admissions. The notion of fairness is very important, especially when decision-making is involved. There are several definitions of fairness. Are there necessarily so many different views? What is the best way to define algorithmic fairness? Having many different definitions, what does it mean to be fair after all? These are all open questions. In this context, it is also very important to see how the general public views fairness criteria in algorithmic decision-making. By testing people's perception of different fairness definitions, we can understand definitions of fairness that are appropriate for particular contexts. One such attempt investigates which definitions people perceive to be fair in the context of loan decisions and whether fairness perceptions change with the definition of a sensitive information. Overall, calibrated fairness, one definition of fairness, tends to be more preferred than others in this particular experiment. We have seen that approaches to tackle unfairness or ensure a fair outcome fall into different categories. Within each category, several approaches already exist. It is still very early to say which one works best for which context. There is no evaluation of these approaches that puts them all under the same lens. So there are generally not conclusive results as to which fare better. It could be the case that a combination of methods should be applied, for example, a pre-processing step and in-processing step. This is also an open question as different efforts have adopted a single angle in the problem. Finally, while a lot of work is done in a research setting, we still do not see many actual applications and their results. There are many challenges in making algorithms and systems fair in the real world. A company, for example, needs to consider its business metrics, for example, click-through rate, purchases, and so forth, and make sure that these are not affected. How do we design algorithms that take into account all these different objectives, and how do we evaluate them? I would like to finish with an example of a real application of fairness in LinkedIn, where they developed a FAIR framework and they applied it to LinkedIn talent search. Online A/B tests showed tremendous improvement in the fairness metrics without a significant impact on the business metrics, and that's why they deployed it to LinkedIn users worldwide. Fairness has many different meanings and challenges. Thank you for watching this tutorial.
Okay, so thank you so much for the tutorial. And I guess I would like to ask, are there any questions before we adjourn here? Any of the participants? Again, you can go ahead and raise your hand if you would like. Okay, so any last words from any of the presenters?
Thank everyone for attending the talk. The slides are available if you want to take a look at the slides. We will post the Google site in the Slack if you want to look at our slides. And if you have any questions, please use Slack or direct email to us. Thank you.
Okay, well, thank you so much. And I guess with that, we will go ahead and end. Thank you, everyone. Bye-bye.
Thank you. Bye-bye.